Our entire civilization today is built on sand. We took ordinary silicon, ran electricity through it, and made it do our bidding. It sounds like magic, but we call it programming. Have you ever wondered why we call it code? Not text, not instructions, but specifically code? Because at first it really was an encrypted language for the chosen few. A language to communicate with monsters made of iron and tubes, which took up an entire building and consumed the energy of a small town. Today, code is everywhere. It decides what music you'll hear next, how a self-driving taxi will move, and even who your next match on Tinder will be. We live in a world created by programmers, but we know almost nothing about how this world was born. And the story there is just incredible. It features the daughter of a rebellious poet who invented the future on paper. There's a Navy admiral who found the first bug in the system. There are hippies and sweaters who created the foundation of the internet in clouds of cigarette smoke. This isn't just a story about technology. It's the story of how human thought finally broke free from the limits of our biological brains. Hi there, I'm a desperate programmer, and today we're going to take a journey 200 years back, from weaving looms to quantum computing. We'll find out how we went from switching wires by hand to talking with AI. Ready to see how we actually taught rocks to think? Then let's go! Our story doesn't start in Silicon Valley, but in the smoky city of Lyon in 1804. Take a look at this device. This is Joseph Marie Jacquard's loom. Before it, weaving complex patterns was backbreaking work. Jacquard sparked a revolution. He invented a way to record patterns on wooden cards with holes in them. If there's a hole, the hook goes through and lifts the thread. If there isn't, the hook hits the card and stops. This was the world's first binary file. You see what I mean? The fluorofabric you're wearing is the result of the very first algorithm at work. Jacquard didn't just automate labor. He proved that information could be separated from humans and transferred to a machine. 20 years later, these punch cards were seen by Charles Babbage, an English mathematician with a difficult personality and a brilliant mind. He couldn't stand mistakes in mathematical tables, which at that time were calculated by people. "God," he exclaimed once, "how I wish these calculations could be done by steam." Babbage began building the difference engine. It was a gigantic calculator made of thousands of gears, weighing several tons. But the real masterpiece was in his mind. The analytical engine. It was the first true general-purpose computer. It had memory. He called it the store. The processor, which he called the mill, and input through the same Jacquard punch cards. But Babbage saw only numbers in it. He needed someone who could see the magic. Ada Lovelace, the daughter of Lord Byron, the rebellious poet she never knew. Ada's mother, afraid her daughter would inherit her father's madness, forced her to study only mathematics. But poetry still broke through. Ada called her approach poetic science. In 1843, she translated an article about Babbage's machine and added her own notes to it. These notes were 3 times longer than the article itself. In them, she described the first complex algorithm, the calculation of Bernoulli numbers. But that's not the main thing. Ada took a step that was 100 years ahead of her time. She wrote, "The machine can operate not only with numbers. If we can express music or science using symbols, the machine will be able to create melodies or images of any complexity." She realized that a computer is not just a fast calculator, but a tool for processing meaning. She envisioned a world where machines help people create. Unfortunately, Babbage never finished building his machine due to lack of funds, and Ada passed away very young. Her genius remained on paper for centuries. But the spark had been lit. 100 years would pass, and humanity would once again need magical mechanics, but this time for entirely different purposes: war. 1940. Europe is in flames. Nazi Germany seems invincible because their orders are encrypted with Enigma. It was a machine with billions of combinations. A person couldn't break it in a lifetime. To defeat the enemy, the Allies needed not just a soldier, but a mathematician. Alan Turing, the man who changed everything. He realized that to defeat a machine, you needed another machine. Turing created the bomb, an electromechanical device that could cycle through Enigma's combinations at a speed no human could match. But Turing did something even greater. Even before the war, he described the idea of the universal Turing machine. This was a fundamental breakthrough. He proved that a single machine could perform any task, as long as it was given the right set of instructions. This is the modern definition of a computer. Turing gave us the logical heart, but the iron body appeared a little later. 1945, USA. ENIAC takes the stage. It was a real monster. 18,000 vacuum tubes, 30 tons in weight, and an energy consumption that dimmed the lights across all of Philadelphia. But there was one small detail. ENIAC didn't have any memory for programs. Do you understand what that meant? To program ENIAC for a new task, like calculating the trajectory of a shell, operators had to manually reconnect thousands of wires. It was like the work of a frantic telephone operator. Writing a single program could take a week, physically running around the machine with cables in hand. And here we come to a fact that was kept quiet for a long time. Who were these first programmers? Kay McNulty, Betty Jennings, Ruth Lichterman, 6 women whose names weren't even mentioned in the official reports when the machine was launched. The military leadership believed that developing the hardware was complex engineering for men, while connecting wires according to a diagram was simple secretarial work. In reality, these women outpaced the male engineers. They discovered that the machine could be taught logical loops and branching, even before these terms appeared in textbooks. They could feel the code by touch. But this approach couldn't last forever. People got tired of running around with wires. We needed an architecture where the program is stored inside the machine itself, like a thought in your head. This was proposed by John von Neumann, and it paved the way for the next big step: how to talk to the machine without cables in your hands. We started to build a language. After wires came the era of punch cards. These were rectangular pieces of cardboard where each row of holes represented a single command. What did this look like in practice? You wrote your code on paper, then went to a special punch machine and punched your code onto the cards. If your program had 1,000 lines, you had a stack of 1,000 cards. That's a wild story. Imagine getting off the bus, tripping, and scattering your code all over the road. Your entire week's work turns into a pile of garbage that you can't possibly put back in the right order. But even if you didn't drop the cards, you'd hand them over to the operator in the evening and only get the results back the next morning. And if you made one tiny typo, bam, error. Fix it and wait another whole day. Programming was a test of patience. That's where our next heroine comes in. Grace Hopper. Amazing Grace. She wasn't just a scientist. She was an admiral in the United States Navy. She's the one who popularized the term we use every day: bug. On September 9th, 1947, her team was working on the Harvard Mark II computer. There was a malfunction. They took the machine apart and found an actual moth in one of the relays. Grace took it out with tweezers, glued it into the logbook, and wrote, "First actual case of debugging." She was a woman with a great sense of humor. But Grace's real revolution was something else. She was the first to say, why do we have to speak to the machine in its language? Let it learn to speak ours instead? In 1952, she created the first A0 compiler. It was a program that took words understandable to humans and translated them into machine code. Her colleagues told her she had lost her mind. A computer is a mathematical device. It only understands numbers. But Grace replied, we just haven't taught it the language yet. She became the mother of the COBOL language. This language was so successful that almost all of the world's banking systems still run on it today. Every time you swipe your card at a terminal, somewhere in the cloud, Admiral Hopper's legacy responds. At the same time, John Backus from IBM created Fortran for scientists. Now programming became accessible not only to select mathematicians who understood memory structure, but also to engineers and businessmen. But these languages were still tightly bound to specific tasks. The world needed something universal, something that would unite all these metal boxes into one understandable system. The next stop on our journey, the shadowy corridors of Bell Labs and the birth of the god of all languages. The early 70s. While IBM was building giant mainframes for corporations, in the basements of Bell Labs, a group of people in wrinkled t-shirts and long beards were creating the future. These weren't your typical engineers of the time. They were hackers in the best sense of the word. The main characters, Ken Thompson and Dennis Ritchie. It all started with a game. Ken Thompson wrote the game Space Travel on a giant Multics mainframe, but playing it was way too expensive. Every minute of processing cost a ton of money. So Ken found an old half-forgotten PDP-7 computer that had only 8 kilobytes of memory. That's less than the size of a favicon on a modern website. To run his game on this hardware, Ken had to write his own operating system. That's how Unix was born. But writing it in assembly was a nightmare. Ritchie and Thompson wanted a language that was as fast as assembly, but as elegant as high-level languages. At first, there was the B language. Then Ritchie spent several years improving it, adding data types and structures. In 1972, C was born. The C language became the Latin of the digital world. It was incredibly simple, yet gave the programmer complete control over the hardware. It was C that the entire Unix system was rewritten in. It was a shot. Previously, it was believed that it was impossible to write an operating system in anything other than assembly language. Ritchie proved otherwise. But Unix was more than just code. It was a philosophy. Do one thing and do it well. Instead of one huge program that could do everything, Unix consisted of hundreds of small programs that could be connected together using pipes. It was a construction set for geniuses. Where is C today? Everywhere. The Windows kernel is written in C and C++. macOS and iOS are descendants of Unix. Android and Linux are Unix-like systems. The firmware in your refrigerators, automotive systems, even Mars rovers, all of them run C. Dennis Ritchie passed away in 2011, just a few days after Steve Jobs. The world barely noticed his death amid the headlines about the iPhone. But without Ritchie, there would be no iPhones or computers as we know them. He built the foundation on which our entire digital world stands. But while the programmers at Bell Labs were refining their code, a new problem was brewing in the world. Programs were becoming so large that a single programmer could no longer keep the whole structure in their head. We needed a new way to think about code. We needed objects. By the mid-70s, programming was like writing a long list of recipes. Take this, mix it with that, put it over there. But when programs grew to millions of lines, that list became unmanageable. A single small bug in one place could break the whole system. The solution came from a place called Xerox PARC. It was a real paradise for dreamers, where you could find almost everything: the laser printer, Ethernet, and object-oriented programming, OOP. Alan Kay, one of the main ideologists of OOP, had a background in biology. He thought, our bodies are made up of cells. Each cell lives its own life, has its own memory, but they communicate with each other through messages. Let me explain it in simple terms. Imagine you're programming a racing game. Before, you would write, draw the wheel, draw the body, change the coordinates. In OOP, you create an object called car. It has properties and methods. It's like a Lego piece. You know how it works, and you don't need to know what's inside it to build a castle out of it. It was at Xerox PARC that the first true OOP language, Smalltalk, was created. And it was here that one of the most famous events in IT history took place. Steve Jobs came on a tour of Xerox and saw 3 things there: the mouse, the graphical interface, and OOP. Jobs later said that he was so impressed by the icons that at first he didn't even realize how important object-oriented programming was. But it was thanks to OOP that it became possible to create such complex things as Windows. Why? Because in OOP, every window on your screen is an independent object. It knows where it is and how to respond to a mouse click. Later, C++ by Bjarne Stroustrup appeared, which added objects to the C language. Then came Java, which made OOP the standard for the whole world. This was the era when we learned to build programs like complex architectural structures, layer by layer, block by block. But while corporations were building their giant systems, another revolution was brewing in universities and garages. It was about accessibility, about the idea that code should not only be powerful, but also beautiful and easy to read. About the idea that code belongs to everyone. It was the time of Python and open source. The 90s changed the rules of the game. The internet appeared, and we needed languages that would allow us to change pages on the fly. In 1995, Brendan Eich created the JavaScript language in just 10 days. At first, people laughed at JS. Professional programmers called it a toy. But today, it's the most widespread language in the world. Without it, not a single button in your browser would work. This is a story about how speed and accessibility beat complexity. At the same time, Python was gaining momentum. Guido van Rossum created it with a simple idea. Code is read much more often than it is written. He created a language that looks almost like plain English. Python removed the barrier between beginners and programming. Today, everything relies on it, from analyzing black hole data to Netflix's recommendation algorithms. But the main revolution of our time isn't a new language, it's open source, the philosophy of open code. Linus Torvalds created Linux and gave it to the world for free. That changed everything. Today, when you start writing a program, you don't start from scratch. You use libraries and frameworks written by thousands of people from all over the world. We stand on the shoulders of giants. Our modern world, smartphones, banks, airlines, is a giant pyramid built on open source, where every block has been checked and improved by millions of eyes. We've made programming mainstream. We've made it democratic. But does that mean we've reached the end? Or are we just preparing the ground for something that will replace us? We've traveled a 200-year journey, from holes in paper weaving patterns into fabric to neural networks that write code themselves. Today, many people fear that AI will make programming obsolete. Why bother learning syntax if you can just ask a chatbot, make me a website? But remember Ada Lovelace or Grace Hopper. Every step in this story was an attempt to move away from boring hardware details toward pure ideas. Programming was never just about writing text. It was the skill of breaking down a complex, tangled problem into simple logical steps. AI can write code, but for now it can't understand why that code is needed or what problems it's supposed to solve. Programming isn't just a profession, it's a way of thinking, an ability to bring order to chaos. We've taught stones to think. Now our task is to think together with them. The story of programming is just beginning, and you are a part of it. Thank you for taking this journey with me. If you enjoyed this epic story, subscribe to The Desperate Programmer. Give it a like, and let me know in the comments which historical figure impressed you the most. Remember, code is the poetry of logic. See you in the future.